Hello everyone, welcome back to Chapter 10. This is Part 7 of our series on gases. This is Dr. Rhonda Kofelt. And in this part, we are going to look at another law, which is not considered one of the simple laws, but this is the Daltons Law of partial pressures. And we use this, it's kind of reminiscent of stoichiometry because we're going to be relating the mole fractions to the partial pressures of a gas. And we use this quite a bit in the real world. So most of the time when you encounter a gas, it's not just one gas, it's a mixture of gas. So for example, breathing air that's dry with no water in it is going to be 78% nitrogen, 21% oxygen, 0.9% argon, and then 0.04% carbon dioxide. And there could be other things in there, but very, very small quantities. And so these are by and large the largest percentages that we find in there. So since it's a mixture, okay, the way gases work is they're not really interacting with each other. They're just mixing and trying to get as far away from each other as they can. And so even though it's a mixture, we can look at its pressure, volume, and temperature as being one thing because it's just all in there mixed homogeneously together. And if we know the pressure, volume, and temperature, then the total moles of the molecule in the air sample can be determined even though there are different compounds. And we use these molar fractions, as we're going to see, in order to do that. So Dalton's law states, and it's the easiest law in the universe, the total pressure of a gas mixture is the sum of all the partial pressures. And according to the kinetic molecular theory, remember they have negligible size, they don't interact with each other, they're just trying to get away from each other. And so since they have different sizes, then they're going to have they'll have the same average kinetic energy, okay, because they're so small. So if they were big things, it would make a difference. But since they are super small, even though they have different masses, they have basically the same average kinetic energy as long as you don't change the temperature. And since the average kinetic energy is the same, the total pressure of the collisions are the same. So when we talk about the pressure of a gas, it's going to be a partial pressure if it's in a mixture. Okay, so the pressure of the single gas in a mixture is its partial pressure, and we write that as P and then sub whatever it is. So if it's helium and it's got argon, then if that's all that's in there, then that's Dalton's law. The partial pressure of the helium plus the partial pressure of the argon gives us the total pressure in that system. And so you can do it this way, or there's another way of doing it that we're going to look in just a minute. But this is basically, you know, how you'll see that written, and this is a real world example of that. The gases behave independently, okay? They are not reacting with each other. They just happen to be trapped in the same container. And so since any gas is P sub N being whatever that gas is, then each one acts independently. So PV equals nRT, that's what this is, and we rearranged it to solve for P. So the pressure of each gas, the partial pressure I should say, of each gas is still equal to nRT for that gas. So all of this is going to be the same for each one of the gases, but the number of moles is the only thing that may be different. So if you have a multi-component gas, you've got gas A, gas B, gas C, and they all are equal. The pressure is equal to this as it relates to the number of moles of each one of those gases. Okay, so the total pressure, we said, is the pressure of all of them added together. All right, and since it's nRT over V for each partial pressure of gas, then the total pressure is going to be equal to the total number of moles in the mixture times RT divided by V. All right, and when I write it, I usually write nRT over V, just so we don't get mixed up as to where that N goes, okay? But the total will be the total moles times the R times the temperature and the volume of that system. So the ratio of the partial pressure of each gas to the total pressure contributes to the total pressure, and that is equal to the mole fraction of the mixture. Okay, so if this is gas A, all right, gas A divided by total gases, and these are moles, gives us what we call the mole fraction. And the symbol for mole fraction is X sub A if it's gas A. If it was helium, it'd be X sub HE equals N sub HE divided by N total. And we don't multiply it by 100, 100, remember, because when we're doing a fraction, it's out of 1 instead of out of 100. So we're just looking at this, and it'll be a decimal less than 1. Okay, so if you want to rearrange that, you can also look at it as the partial pressure of something like nitrogen, for example, would be equal to the mole fraction of nitrogen times the total pressure. So if you're trying to find that, you know what the mole fraction is and you know what the total pressure is, you can find what that is. You can also flip that, and if you know what the partial pressure of your nitrogen is, okay, in this case we said it's 78%, which out of 100, that's 0.78 out of 1, right? Then that partial pressure times the mole fraction will give us the total pressure. Okay, so maybe and if you need to go back and hear this again, I go through these pretty quickly because I know you can go back and re-listen to them and slow me down and all that. All right, so this first question is going to be pretty simple. You have a 1 liter mixture, and you always make sure you know what that total volume is there. You have a 1 liter mixture of helium, neon, and argon. So you've got 3 gases. You have a total pressure of 662 millimeters of mercury, and the temperature is 298. All right, so I'm going to go ahead and start my inventory. So I've got a volume of 1 liter. I have a total pressure of 662 millimeters of mercury. I have a temperature of 298 K, and then it tells me the partial pressures of helium. My partial pressure is 341. The partial pressure of neon is 112. And it wants to know what is the mass of argon, because that's the third one, okay? Now, when you first look at this, you're like, okay, that didn't give me the partial pressure of argon, but it did give me enough information to figure it out, because it gave me the total pressure and 2 of the 3 partial pressures. So the difference between the total pressure and the partial pressures of the other 2 is going to give me the partial pressure of the argon. So the P total, because this is Dalton's law, right, equals PHE plus PNE plus PAR. So I'm solving for that. So P total minus the helium minus the neon is going to give me the partial pressure of the argon. Okay, so that's 662 millimeters of mercury minus the helium, which is 341 millimeters of mercury, minus the neon, which is 112 millimeters of mercury, and that's going to give me 209. All right, so my argon is 209 millimeters of mercury. So even though it didn't tell me what that was, it gave me the information in order to calculate it. All right, now, when I do this calculation, I'm going to be figuring out the number of moles because I've got volume, pressure, I've got temperature. I know what R is, 0.0821 liter atmosphere over mole K. So I've got everything I need to find the number of moles, and this would be the total number of moles if I used the total pressure. And I could do that and then subtract. But it wants to know the mass of argon, and I told you when you see mass, you think moles, right? So I know that I can calculate the number of moles using the ideal gas law. And so if I have PV equals nRT, I know what the pressure of my argon is. Now my argon is going to have to be changed into atmospheres, right? 760. Okay, and that would give me 0.275 atmospheres. Why do I do that? Because when I put it in here, they've got to be in the same units as R, remember. All right, I'm solving for N. So N equals PV over RT. So that equals 0.275 atmospheres times my volume, which is 1 liter, divided by R. Times the temperature, which is 298. Okay, and so when I do that calculation, I'm going to get 0.0112 moles of argon. But remember, I'm not done yet because what's it asking me for? It's asking me for the mass. So I have to do one more step, 0.0112 moles of argon times, and I have to look up and see what is the formula weight. The formula weight of argon is 39.95. So 1 mole has to go on the bottom so it'll cancel. 39.95 grams on the top. And that is going to give me 0.449 grams of argon. So I used Dalton's Law first to find out what the partial pressure was. And then all I had to do was then plug that pressure because I was looking for argon. Because remember, the volume and the temperature in R are all still going to be the same, only the pressure and the number of moles will be different. So that's how I can plug that in and find it. You could have solved for the total and then subtracted at the end, but to me it's easier to do it up front and then you just have to plug and play. Okay? So that's total pressure and partial pressures according to Dalton. I have given you one that's similar. Remember, torr is the same thing as a millimeter of mercury. Okay, so they have the same what am I saying? Units, the same magnitude. 760 torr and 760 millimeters of mercury. Okay. All right, and so you have a practice problem, and that is your first scenario of total pressure and partial pressures. Now, that second one, it gave you something. Let me give you a hint on this. It says it's doing something with water vapor. When you have a problem that says it's got water vapor in it, you're going to subtract that from your total pressure. So the actual total pressure is going to be the 755 minus 24, right? So just keep that in mind because that's going to be the 731. That'll be your total pressure, because water's not a gas. So you got to take that out. Okay? Just a little hint. All right, and that's it for your first foray into total pressures and Dalton's law of partial pressure.